Hello everyone, welcome to IMS Academy. My name is Vipin Mishra and I welcome you all in this foundation course of EMFT, and it is going to be the lecture number 7. Up till lecture number 6 we have studied the vector calculus, we have seen some surface volume line integral, the concept of divergence, curl and gradient as well. We have discussed electrostatic part 1 in lecture number 6 as well, and in this lecture we are going to discuss the remaining part of electrostatic. Now before I start the lecture, if you haven't joined our Telegram channel, join the channel immediately. Okay, also subscribe the YouTube channel, like and share the session, and join this Telegram channel immediately. The link is given in the description box so that you can get the notes of the class immediately after the class ended, and the regular quiz, daily quizzes related to GATE, and the news feed about the PSU job notification and everything related to GATE. Okay, so join the Telegram channel first of all. Now let me proceed. So up till lecture number 6 we have discussed electrostatic part 1. Okay, so followed by coordinate system, line, surface, volume integral, gradient, divergence and curl, and then we started electrostatic. In this lecture we will try to finish the electrostatic part 2, and then in the following lecture we will discuss magnetostatic and Maxwell equations. So this is the schedule or the lecture flow that we have, and you are watching currently the lecture number 7. So lecture number 6 we ended with Gauss law. So what was the Gauss law? Let me just read the statement. So the surface integral of the normal component of electric flux density d over any closed surface equals to the charge enclosed, isn't it? Means if suppose you are calculating the surface integral of d dot ds, then what's gonna come? It will be equal to the total charge enclosed inside the body. Okay, this law is applicable for volume, okay, surfaces that bound some volume. Okay, so inside the surfaces that bound some volume, the total flux, you may also call charge as a flux as well. So the total flux coming out from the closed surface is basically equal to the charge enclosed inside the surface, or you can just read the first statement, the surface integral of normal component of electric flux density, that is d, is equals to the charge enclosed. Surface integral d dot ds equals to q. This is the statement of Gauss law. Okay, this is what we have discussed yesterday as well. Now you people know that q, if I want to write q might be written as, if suppose I want to write the volume charge density, so volume charge density will be del q over del v, charge per unit volume, some infinite small charge enclosed by some infinite small volume, the ratio of them will give us the volume charge density, isn't it? So volume charge density might be written in this way. So in this way, you know, we can write the small charge like this, and if I want to calculate the total charge, I might be calculating the total charge in this way. It will be volume integral rho v dv. So charge might also be written in this way. You know that surface integral d dot ds is equals to q, and q is equals to rho v dv. That means we can equate these two quantities. Surface integral d dot ds, which is equals to q, is also equals to volume integral rho v dv, where rho v is the volume charge density, isn't it? We can write it in this way. If you are writing this formula, it is also known as the Gauss's law in its integral form. So this is basically the integral form of the Gauss law. Another way of writing the charge. Charge might be written in terms of the volume charge density as well. And charge is also, as per the Gauss law, the charge enclosed inside the volume is surface integral d dot ds. So we can equate these two things. Now as per the concept of divergence, what do we know? If suppose I want to calculate the divergence of d. So if I am calculating the divergence of d, it will be limit del v tending to 0, and what you will do, you will just do this thing, surface integral d dot ds divided by this small volume. Okay, this is how we calculate the divergence, isn't it? This is how we calculate the divergence. We discussed the concept of divergence. In that video you can find this. So the divergence of any vector quantity, if you want to calculate, this is how we will be doing. Surface integral of that quantity divided by the small volume. Okay, This is how we used to calculate the divergence. Now, as I have written the divergence is equals to this quantity, this will be equals to rho v. How? Just see. So, what we can write for d dot ds? Surface integral d dot ds. Okay. So, what you will write for surface integral d dot ds? Just see, surface integral d dot ds is basically equals to q, and q over volume is what? Is rho v, isn't it? So, can we write that divergence of d is basically equals to rho v, or what we have concluded is this thing, that del dot d, this is equals to rho v. An important observation we have calculated here, we have found out. While calculating the divergence of d, we have calculated that it is equals to rho v, the volume charge density, isn't it? If there is no charge enclosed by the surface, del dot d will be equals to 0. Divergence of d will be equals to 0, isn't it? So, the divergence of d gives the free charge density at a point. If the charge is 0 at that particular point, followed by the charge density to be 0, and then we will be having the divergence of d equals to 0 at that particular point. So, divergence of d will give us something that depends upon whether there is any charge enclosed or not, okay, by the surface. When the divergence of a vector is non-zero, the region is said to contain either a source or a sink, isn't it? What is divergence? Divergence is basically the net outward flow of the flux related to that particular quantity, isn't it? When the volume is shrinking, it appears that the flux related to the quantity is emanating from that particular point source, isn't it? So, related to the divergence concept, if the divergence is 0, that means there is no net outward flow when the volume is shrinking. But if the divergence is not 0, that means there is either net outward flow, so means the point is acting as a source, or there may be the case where the point might be actually acting as a sink, isn't it? For example, just see this example. You know about the positive charge. So, if suppose we have some positive charge, so around this positive charge it appears to be like this, isn't it? That we have field lines all around this charge. So, just see, these field lines appears to be emanating from this point source, isn't it? Plus q. So, what will happen? In this case, we will never have divergence of d equal to 0, because it is acting as a source. The flux emanates from this point source, isn't it? Similarly, if suppose I would be having negative charge, if suppose I would be having some negative charge, so around the negative charge the flux appears to be coming towards it. The flux appears to be coming towards it, so it will be acting like a sink, okay, but the difference will be del dot d when you will calculate here will give you positive, okay, del dot d, or you may also write it del dot d, it will give you positive result, but here del dot d it will be negative, because the point source is acting as a sink, isn't it? Hello Chaitanya, hello Naveen, okay, is that clear? So, if the divergence is not 0, that means there is some net outward flow of that of the flux related to that particular quantity in which we are interested. If the quantity is emanating from the point source, it appears to be that divergence will be positive, or the thing is acting like a source. If the quantity is getting into the body or the point source, it appears to be the divergence will be negative and the things will be acting as a sink, okay. So, we have calculated the divergence and we found out that it will be equals to the volume charge density. That means if there is a flux, if there is a charge associated with the body, divergence of d will not be 0, isn't it? And the things might be acting as a source or sink, depends upon the divergence value as well. So, del dot d is equals to rho v that we have calculated, and you know that d is equals to E epsilon. So, we can also write that del dot E, this will be equals to rho v over epsilon. So, this might also be the formula, and when you are writing the Gauss law in this format, it is said to be the Gauss law in its differential form, The Gauss law is in its differential form. Okay. Now after that, so finally what we have concluded is Gauss said that surface integral d dot ds equals to q. The charge enclosed by a surface having some volume will be equals to the d dot ds equals to q. Okay. Or we can say that the surface integral d dot ds equals to the charge enclosed by the surface. Okay. And q is equals to rho v dv, volume integral rho v dv, and rho v now we have calculated that it is del dot d. So finally we can write del dot d dv. So what we have concluded here right now, that if you are calculating charge enclosed by the body, this will be equals to closed surface integral d dot ds, or this will be equals to the volume integral del dot d dv. This is the important conclusion that we have drawn here. Okay. So in this way we can calculate the charge enclosed by the body, either by calculating the surface integral of electric flux density or by calculating the volume integral of divergence of d dot dv, or we can also write it del dot d upon del dot e. Okay. So whatever way you want to write it. So if you are writing it in this format, this is known as basically the divergence theorem as well. Okay. And the divergence theorem states that the integral of the normal component, that is d, of any vector field over the closed surface is equals to the integral of divergence of this vector field throughout the volume enclosed by the closed surface. Okay. So if you are calculating the integral of normal component of any vector field, okay, if you are calculating the integral of normal component of any vector quantity, any vector field over the closed surface, okay, means we are calculating the surface integral over any closed surface of that particular quantity, that will be equals to the integral, volume integral of this field calculated by using the divergence as well. Okay. So this is also known as Gauss divergence theorem as well. Okay. So this is what we have learned in Gauss theorem, and as per the consequences we can also draw these consequences, that surface integral d dot ds means the surface integral of any vector field along the closed surface equals to the charge enclosed is also equals to the volume integral rho v dv, or also equals to the volume integral del dot d, divergence of that vector field evaluated around the volume. Okay, means volume integral of del dot d dv. Okay, this is also known as Gauss divergence theorem, which is very important and might be used so many places. Okay. Now the second topic, important topic, is potential difference and potential. So let's understand the potential difference and potential. If suppose we are having electric field, okay, if suppose we are having electric field, then what do you know if suppose in this electric field I have a positive charge. So if there is a positive charge placed in this electric field, what will happen to this positive charge? It will feel a force in the direction of the field, isn't it? But if suppose I have a negative charge, it will feel the force opposite to the direction of electric field, and this is what is written here. A charged particle placed in an external field will experience a force, and that force experienced by the charged particle is in the same direction as that of electric field if the charge is positive, and it will be opposite to the electric field if the charge is negative. So if suppose in the electric field we have a charge, that charge will feel a force in the direction of the field, and that force will be Q into E if it is a positive charge. Now it will feel a opposite force if it is a negative charge, opposite to the direction of field, okay, if it is a negative charge. So this is a simple concept, we should know this. If we have the positive charge, it will feel a force in the direction of electric field. If it is a negative charge, it will feel a force opposite to the direction of electric field. Okay. Now after that, let's see. If we try to move a positive charge Q against E, work is required to do this. Okay. Just see, if again I have the same electric field. Okay. If I have the same electric field. Now if suppose there is a charge and you are moving the charge from point P to point Q. Okay. Now this charge is either moving in the direction, in this direction P to Q, or in this direction P to Q. Let this distance is del x. Okay. So if the charge is moving in the direction of electric field, the work is done by the field. If the charge is moving against the direction of field, external force needs to supply some, external force need to just supply some work, isn't it? External force will give some energy, external source will give some energy to just move against the direction of field. But in both the way, work is being done either by the field or by the external source. So if I calculate something called as work done per unit charge, then how can I write the work? Work is basically force into the distance. So how much distance we have moved? Del x divided by Q. Now what is F upon Q? What is force upon Q? Is electric field intensity. So we can write it E dot del x. And now this quantity E dot Lx is, E dot del x is known as V. So ultimately what we have calculated is that work per unit charge, work done per unit charge is basically equals to V, and that V is known as the electric potential. Okay. So if the charge is moving in the direction of electric field, the work will be done by the field. If the charge is moving against the direction of the field, some external source will be giving some energy, and that's how it will be moving against the direction of the field. Okay. Now, as I told you, if there is a positive charge moving along the direction of the field, work will be done by the field, isn't it? Work will be done by the field, since the force exerted by the field on the charge will be in the same direction of the movement. Okay. But if the charge is moved against the direction of the field, external agent needs to supply energy to the charge in doing so, isn't it? As I told you, if the charge is moving in the direction of the field, because the movement is naturally in the direction in which it should be, consider positive charge, then the work is being done by the field. But if suppose the same charge, positive charge, is moving against the direction of the field, so it is moving against the direction, natural direction where it should be moving, then some external source needs to supply some energy so that the charge can move in the opposite direction. I hope you understood. Okay. Now what is very important is, okay, the work done by the external source to move the test charge against the field is always taken as positive. If some external source is supplying some energy to the charge when it is moving against the direction of the field, that work will always be taken as positive. Okay. If the charge is moving in the direction of the field, work is done by the field, that work with respect to the external source will always be taken as negative. Okay. Let me take a condition. Just see. If suppose we have some electric field, let us suppose this is the electric field that we are having. Now in this electric field, there is a positive charge placed here. So what will happen? The field will apply a force on this charge in this direction, which will be equals to Q into E. Now naturally the positive charge will be moving in this direction, isn't it? If suppose, so work is being done by the field. If suppose you want to move it opposite to the direction of the field, external source needs to supply energy, isn't it? And that work which is done by external source, we will take it positive. And that work which is done by the field with respect to the external source, it will be negative. Let us consider that right now the charge is at the position P, and we are moving this charge from this position P to some position Q. We are moving it from position P to position Q, and while that it travels some distance dl, and it is making some angle theta like this. Okay, it is making some angle theta in this way. Then can you tell me how we will write the work done on this small charge? Let us suppose we have some small charge, then what will be the work done by the field on this charge? So the work done by the field on this charge will be, if I am writing this to be dw, okay, then this will be what? This work dw will be f dl cos theta, isn't it? It will be f dl cos theta. Now what we can write for f? F can be written as q into e, dl cos theta, or what we can write, q is a scalar quantity, we can write it e dot dl, dot product of e and dl, which is e dl cos theta. We can write it in this way. Okay, we can also write this in this way. So this is the work done while moving the charge from P to Q. Okay, now see, if this theta angle is in between 0 to 90, what will happen to this work? This work will be positive. But if this theta is in between 90 to 180, then what will happen to this work? This work will be negative, isn't it? So just see, naturally the work done by the field, if we are calculating, if theta is 0 to 90, that means it is moving in the direction of field somehow, then what will happen? The work that we have calculated is coming out to be positive. If it is moving opposite to the direction, the work that we will be calculating is coming out to be negative, isn't it? So that means the external source which is supplying energy while moving the charge opposite to the field, okay, it's actually supplying the negative force. If you are considering that positive work done, then this work done which is required to move the charge in the direction of field will automatically taken as negative, and this is the reference we take while calculating the potential. Okay, the work which is done by the field will be taken as negative, the work which is supplied by the external source will always be taken as positive. Okay, so here we have considered positive charge, so naturally it will be moving in the direction of field, so we will consider this work to be negative. Okay, now see, so what we can conclude is differential work done by external source in moving the charge q will always be minus of q e dl, isn't it? Just see here, naturally when theta is from 90 to 80, 180, it will be moving in this direction, yes or no? So that natural work is coming out to be negative. So this amount of work needs to be supplied by the source, isn't it? By the external source. So the differential work done by the external source in moving the charge q will be dw equals to minus qe dl, that we have just calculated. Now if the charge is moved a finite distance, suppose from P to Q, then the work done will be always written in this manner. Okay, just see, w will be minus of q P to Q e dot dl. Okay, work done is dependent only on the coordinates of end point and not on the path. Okay, because electric field is a conservative field, we will see that. So what is this meaning? If suppose we have some point P and some point Q, then the work done only depends upon the coordinate between the point P and Q. Okay, it does not depend upon what path we are following to go from P to Q. Okay, so does not depend upon the path. It does not depend upon the path followed. It depends upon points. Okay, it depends upon P and Q, the location of the points P and Q. It does not depend upon what path we are following. So in all the way, if you will calculate, the work done will come out to be the same. Okay, so the work done by the external source dw for moving the charge against the direction of the field, okay, naturally it is coming negative. Okay, this is the work that external source is doing. Fine. With respect to it, the work is done by field will always be taken negative. Okay, So the work done W is basically the gain of potential energy associated with the movement of charge from P to Q. Negative sign will have potential rise, and if suppose positive sign, if negative sign is removed, means positive sign is coming, it will be indicating the fall of potential. Okay. The potential difference V is defined as basically the work done per unit charge, okay, from one point to another point. So the potential difference V is basically W by Q, or which is minus initial to final E dot dl Q. This is how we will write. Suppose we have an electric field. Okay. So if suppose we have electric field like this. Now in this electric field, if suppose I am moving my charge, let's suppose this is point P and this is point Q. If suppose I am moving my charge from P to Q, okay, then how I will be writing it? It might be written as the potential VPQ, and it will be calculated like this. What is the initial point? Just a correction. If suppose I am moving from Q to P, okay, then it will be PQ. So let me change the position of the points. If suppose this point is P and this point is Q, and I am moving from Q to P in this way, okay, then the potential might be written as VPQ, and it will be calculated. Q is the initial point, P is the final point, E dot dl, okay, from Q to P, E dot dl. This is how we will be calculating the potential. VPQ will be minus Q to P E dot dl. So whenever you are writing VAB, it should be B to A E dot dl. This is how you will calculate this integral. Okay. So this is how we will calculate the potential difference or the potential as well. Okay. Now potential due to a point charge. Now this is very important, and you will get a very important learning here. Potential due to a point charge. Let us suppose that we have a point charge. So let me consider a point charge. So we have a point charge plus Q. So now what will happen? This point charge will have electric field all around. Yes or no? This point charge will have electric field all around itself, like this. So it has electric field all around it. Okay. So we have considered a positive charge which has electric field all around it. So in the influence of this electric field, okay, let us suppose that we are moving from some point B to some point A. In the influence of this electric field, we are moving from some point B to point A. So if suppose we are moving from some point B to some point A, let's suppose the distance of point B from here is RB, and the distance of point A from this point source is A. And what you are doing, you are moving from point B to point A in this way. Then what is the work done and what will be the potential difference when we are moving from B to A is what we need to calculate. Okay. This is what we need to calculate here. So tell me how you will calculate this potential. So since we are moving from B to A, we will write it AB. Okay, VAB, and this will be minus of initial minus final. So B is the initial point, A is the final point, and we will calculate it like E dot dl. Okay, E dot dl is what we need to do here. Now just tell me how this will be transformed. So B means the distance RB, A means the distance RA. How you will write E? E will be Q upon 4 pi epsilon R square, unit vector R we can take. Okay. Field at any point, let's suppose this is the point, then field at any point is radially outward like this. Okay. It will be radially outward like this. So this is the electric field that we have. Now how to write dl? What coordinate system we will be using here? Cartesian, spherical or cylindrical? Just see this point source you may consider for point source, you will always consider a spherical coordinate. It might be considered as a sphere. So spherical coordinate is what you will be choosing here. So what will be dr? dl will be dr unit vector r. Okay, we practice that how to write this, or r d theta unit vector theta plus r sin theta d phi unit vector phi. This is how you will write dl. Now we have to do the dot product, so only r will give us something. So what we can do, we can take q upon 4 pi epsilon out, and it will be rb to ra, and then we will be having 1 by r square dr. And then finally what we can write it, we can write on solving, it will give us q upon 4 pi epsilon 1 by ra minus 1 by rb. So this is the potential VAB that you will get when you will move the point charge from, when you will move under the influence of the electric field of this point charge. So this is how you will calculate this potential. Okay, potential field of a point charge, how you will calculate potential difference while moving from one point to another point under the influence of the electric field of a point charge, isn't it? Now in this case we are moving from one point to another point, isn't it? Now let's suppose one point, suppose B is at infinity. So if B is at infinity, then what will happen? RB will be infinite. So if suppose we are moving from infinite and we are coming from infinite to the influence of electric field, in that case what will be the potential difference? In that case the potential difference will be q upon 4 pi epsilon ra only, isn't it? So from the infinity, if you are moving from infinity and coming into the influence of the electric field of a point charge, this is how you will be calculating the potential, q upon 4 pi epsilon ra. This will be the potential. Okay, so I hope you got it. Now after that, let us calculate the gradient of electric field. Okay, so I hope this point is clear. Now after this, let us calculate the gradient of electric field. So again consider the same positive charge. If suppose I have some positive charge, if suppose this is the positive charge that I have, okay, so this is the positive charge plus q okay. Now this plus q will have electric field all around it. Let me draw that. Okay. Now let us consider some equipotential surface around this positive charge. So if we are considering some equipotential surfaces around this positive charge, okay, let us suppose at a distance RA we have this potential surface where we will be having the same electric field and potential everywhere, okay. And let us suppose that we have another equipotential surface which is at a distance B apart, okay. So if we have the potential of this surface as V, then potential of this surface will be some V plus del B, okay. Now if we are moving from one surface to another surface, if we are moving on one surface to another surface, let us suppose that we are calculating a distance of dl, okay, then you know that where do we get the maximum rate of increase of this quantity? That we will get in the normal direction, isn't it? So dV upon dl, the rise in the potential we will get in normal direction. So dV upon dl unit vector r, this will give us what? This will give us maximum rate of potential, isn't it? And what do we call this quantity? dV upon dl unit vector n. We have covered the concept of gradient. Okay. So what do we call this quantity? dV over dl unit vector n. This will be called as the gradient of this quantity v or del v, isn't it? This will be called as the gradient of this quantity v or del v. Yes or no? Isn't it? And if we are calculating the maximum rate, okay, then what is the maximum rate of the potential? The maximum rate, if you have to calculate, that will be dV upon dl, or what you can just write it, the amplitude of del v, the gradient of v, isn't it? All these concepts we have covered when we have discussed the gradient. In the gradient we have taken even the same example as well. So what is the gradient representing here? Okay, gradient, what it representing, what is it is representing here? So the gradient of v, okay, the gradient of v, or we can say del v. Just see, earlier what we have seen here, that E dot dl is basically v, isn't it? E dot dl is v. So what is v? V is basically E dot dl. So v is E dot dl, that means del of v, what it will give you? It will give you minus of E. Okay. So this is something very, very important. Gradient of v is basically equals to minus of E. Gradient of v is basically equals to minus of E. Gradient has the direction opposite to the field because of the minus sign that we are getting. Okay. So gradient of v, gradient is having direction, and because of minus we are getting, gradient of v will have a direction opposite to that of E because of the minus sign that we are getting here. Okay. So whenever we are calculating the gradient, it represents the maximum rate of increase of that particular quantity, and where this happens, it happens in the normal direction, isn't it? The magnitude is representing the maximum rate of potential or the maximum rate of growth of that quantity. This is known as gradient of that quantity, and as per the potential concept that we have discussed, the gradient of v will be equals to E, isn't it? Minus E, because this will happen opposite to the direction of E. Okay. So this is the gradient of electric field. Now after that, Poisson's and Laplace equation. Let us discuss the Poisson's and Laplace equation, a very important concept as well. So up till now what you have discussed? Just see, we have discussed that del dot D is equals to rho v, and who told that? Gauss. Okay. Or we can write del dot E equals to rho v over epsilon. So this is what we learned from Gauss's law. Del dot E equals to rho v upon E, and we have also seen that del of v, gradient of v, this is equals to minus of E. Okay. Now let us multiply del on both sides. So if we are doing del dot del v, this will be equals to minus of del dot E. Okay, del dot E. Now del dot del will be del square v, and del dot E is basically minus of rho v upon epsilon. Now del square v means d bar square upon d bar x square v plus d bar square v upon d bar y square if we are using Cartesian coordinates. Okay, this is equals to minus rho v upon epsilon. So if you have written some equation like this, this is known as the Poisson's equation. Okay, this is known as the Poisson's equation. Okay. Now in this Poisson equations, it might happen that if rho v is 0, there is no charge, means charge density is 0. In that case, what will happen to this equation? This equation will be del square v, which is equals to minus rho v over epsilon. This will become 0. Okay. and when you are writing an equation like this, it is known as the Laplace equation. This is called as the Laplace equation, and Laplace equation is valid for free space region, isn't it? Where there is no charge free region we can say. Poisson equation is for that particular region which has some charge, okay, and Laplace equation is for that region which is having no charge associated with it, okay. So this is Poisson's and Laplace equation. Another important thing, now see Maxwell's curl equation, okay, very important. Maxwell's curl equation for a static electric field. So again I am going to consider the same case. Let us consider that we have some point source, okay. So if suppose I have some point source, now this point source, what it will have? It will have electric field all around, okay. So this point source, it will have electric field all around. Let me consider that electric field. So this is the point source which will have electric field all around it, okay. Now under the influence of this electric field, let us suppose I am considering a point B here and I am considering a point A here. So I am under the influence of this electric field, I am moving from point B to point A while going through a path C, or I am moving from point B to point A while traveling through the path D, while traveling through the point D, okay. So in this way I am moving from point A to point B, okay. So these are the two paths that I have taken. First I moved along BCA in order to move from B to A, then I moved along BDA in order to move from B to A. So these are the two paths that I have followed, okay. Now if I am following these two paths, so for moving from B to A, for moving from B to A. So if you are moving from B to A, what will be the potential difference? If I am writing this to be VAB, that will be minus of, if you have taken BCA path, okay, E dot dl you can write, okay, or if suppose you have taken BDA path, you can take that path as well, and the potential is not going to change because potential difference depends only on the path, only on the points, not on the path. That's the point that we have discussed. Just see this point, okay. The potential or the work done depends upon the points, not on the path, okay. So on that particular basis we can write that if you are following BCA path or you are following BDA path, both the work done will be the same, isn't it? And if you can write this, then what you can do, just see, you can just write this equation in this way, that minus BCA E dot dl plus BDA E dot dl, that will be equals to 0, just forming an algebraic equation. Or what you can do, you can write it BCA E dot dl minus BDA E dot dl equals 0, isn't it? We can write it in this way as well. Then what we can do, just see, we can change this BDA to ADB and that minus will become plus, isn't it? From the integral calculus, you know that if I change this sign from minus to plus, the path will be changed. Instead of BDA, it will be ADB E dot dl, that will be equals to 0. Just see, BCA ADB, isn't it? And the same thing we are integrating. So can we write it BCA ADB, isn't it? And E dot EL when evaluated under this path will give you 0, isn't it? So just see, if you are following the closed path BCA to ADB under the influence of electric field of a point charge, the potential that you are getting, potential difference that you are getting E dot dl is becoming 0, and this is the basis of applying KVL in electric circuit, my dear friends. Okay, this forms the basis of applying the KVL in the electric circuit. So when you are following the closed path, what is the potential difference? It's coming out to be 0. It's coming out to be 0. And do you know what it indicates? E dot dl equals to 0. Okay, you obtained E dot dl equals to 0, and it indicates that electric field is conservative. Okay, so E dot dl, now it has become a closed path. You are following a closed path. So closed path E dot dl is equals to 0. Whenever you are evaluating a line integral around a closed path and it is giving you a 0, that means the vector field is conservative. Okay, so it gives us that electric field is conservative. Okay, electric field is conservative. Whenever you are integrating line, whenever you are calculating line integral around a closed path and it is giving you 0, that means that particular vector field is conservative in nature, isn't it? This is what we have just seen here. Now after that, let me ask you one thing. If suppose you are calculating the curl of any quantity, then the curl of any quantity, we have discussed that particular as well, is evaluated by something like this. Okay, now you have found out that line integral is equals to 0, closed line integral is equals to 0, and that indicates that del cross E is also equals to 0. So my dear friends, you have calculated that del cross E is equals to 0. The curl of electric field is equals to 0. The curl of electric field is equals to 0. Yes or no? And that is known as Maxwell's curl equation for static electric field. So if you have a point source which will have electric field all around it, isn't it? It appears that the flux of this vector field emanates from a point charge. It's coming out from the point charge, isn't it? It's like radiation from the positive charge, or it's like net outward flow. So whenever such a scenario is there, divergence will always be there. It will not be 0. So del dot E is not equal to 0. Never ever it will be 0. And is there any rotational motion you can find here? No, there is no rotational motion. So since the absence of rotational motion, del cross E has to be 0, and which you can see it's coming out to be 0. It's coming out to be 0. Okay, so dot product means del dot D, divergence of E, del cross E, curl of E. Okay, so what we have seen, this is also known as divergence of E. Divergence of E is not equal to 0, and it is equals to rho V upon epsilon. And what we can see, that curl of E is always equals to 0, and you have calculated gradient. If I talk about del V is equals to minus E. Okay, so just see the divergence, the curl and the gradient associated to an electric field, how they are responding. How they are responding, you can just have a look here. Okay, so this page which is open in front of you right now is a very important page conceptually from the exam point of view, okay, and from the interview point of view as well. Whenever you will go, these questions will be definitely asked to you. Fine. So this is what we have seen about the potential, and we have seen in general about the electric field as well. Now another important concept of electrostatic, which is capacitor and capacitance. Okay, so a capacitor is basically a device that stores energy in electrostatic domain. It consists of two conductors separated by some insulating material, okay, separated by some distance. Its capacitance is defined as the ratio of the charge on one of the plates, okay, or one of the conductors divided by the applied voltage, or C is equals to basically Q over V. Okay. Now you can see the charge, you can consider from here that capacitance depends upon the charge and voltage. No, The capacitance of the capacitance depends on the physical dimensions, okay, and the nature of insulating material, its permittivity and independent of charge and voltage. So C is equals to Q over V, and this is also equals to epsilon A by D, or we can write epsilon naught epsilon R A by D. So capacitance does not depend only on charge and voltage, even it does not depend upon this quantity. In fact, it depends upon the physical dimension, means A, the area and the distance between the plates, and it also depends upon the medium, relative permittivity. It depends upon the medium in which between the plates as well, okay. So this is what you can just refer about the capacitor, okay. Let me give you a simple example. So just see, we will be having parallel plate capacitor is a normal example that I can give you. Just see, let us consider that this is a parallel plate capacitor that we have, okay. Now this plate and this plate will be given some potential. So let us suppose that this is the applied voltage between them. Now the moment, and this is the distance between them. The distance between the plates is D, and the area of the plate, cross section of plate, is A. Now when you will apply the potential, what will happen? The plates will get charged. Okay, the plates will get charged like this. The plates will get charged like this, and in between the plates there will be some insulating material that we will be having, okay. Now if suppose you want to find the capacitance, that will be Q over V, isn't it? The capacitance will be the charge divided by the applied voltage, okay. Now since you can see, we are, if you watch this plate carefully, it's like an open surface, yes or no? If you see this plate, it's like an open surface. So with open surface, let us suppose that it is having some surface charge density related to rho s. Let us suppose that any of the plate is having some surface charge density rho s. Now how to write Q in terms of rho s? So Q will be rho s times del s. Yes or no? Surface charge density is charge divided by area, isn't it? So let me write area here. Charge divided by area is surface charge density. So surface charge density into area will be the charge. Yes or no? So we can write the charge in this way. Divided by the potential. Potential V. V might be written as E dot dl. Everywhere we have seen. So in general we can write it E dot el. Now just see this rho s over E. You have seen that del dot E is equals to rho V, isn't it? So from there, if you just visualize the things, del dot E was equals to rho V, or rho V upon E will be what? Epsilon, isn't it? So shall we write it epsilon? Yes, we can write it epsilon, and it will become epsilon A by D. And epsilon, you know that it is equals to epsilon A, epsilon R, A by D. So just see. This is how we calculate the expression for the capacitance. C is equals to epsilon naught epsilon R A by D. What is epsilon naught? Permittivity of free space, which has this value, and what is epsilon R is the relative permittivity of the medium. It is the relative permittivity of medium. Okay, so just see. So capacitance does not depend upon the charge and the voltage. In fact, it depends upon the physical dimensions of the plate, that is the area of cross section and the distance between the plates, and the relative permittivity, that means the medium in between the plates. Okay, so this is about the capacitance, as you can see. Now let us talk about the energy associated with electrostatic field or with a charge distribution. Okay. So energy is basically, we write it by WE, and this is equals to the volume integral of, it is equals to the volume integral of electric flux density and electric field intensity, the dot product of them, dV. Okay. Now you know that D is also equals to epsilon E. If I am going to write this, what it will become? It will become epsilon E dot E dV, or it will become epsilon E square dV. Okay, and I forget to write an half here, half is also there. So it is half epsilon E square dV. Okay, volume integral half epsilon E square dV. So energy, that is WE associated to electrostatic field, is evaluated by this particular integral or by this particular formula. So this is the energy associated with the electrostatic field. Okay. So guys, today what we have discussed? We have discussed today the broader aspect of the Gauss law. We have seen the integral and differential form of the Gauss law. After that, we have discussed about the electric potential. Okay, we calculated the potential when we are moving from one point to another point under the influence of the electric field of a point source. After that, we have seen the Maxwell's curl equation. We have seen the gradient of potential is equals to minus of E. We talked about the capacitance. We talked about the energy associated with the charge distribution as well. Okay. And this is how it is the end of electrostatic part 2. So these are the concept. Now what you can do, you can just practice the relevant PYQs. All of them will be covered through these concepts, whatever we have discussed in the last 2 classes. And in this way, you can just be comfortable in electrostatic. Okay. So guys, if you have really liked the teaching and learning methodologies of IMS GATE Academy, it is highly recommended for you to just buy our online course for GATE 25 and 26. We are offering 800 plus live hours of classes. We are giving you some quality materials in terms of theory book, exercise book, and GATE question bank that contains 34 years of questions with video solutions as well. GATE is a very long journey, so you need constant motivation and strategy as well. So we are offering you personalized mentorship session. You can anytime talk to us. You can have a strategy. Okay. We are also offering we are also offering 130 plus online tests as well. Enough number of tests are there. So exercise book contains 4,000 questions, test series contains 3,000 questions. If you practice that many number of questions, you can just do better in any of the exam of the world related to engineering. Okay. So if you wish to join us, this is how, on calling these number, you can just book a counseling session. The details are also given in the description box. Last but not the least, this is the end of this lecture. We will come and discuss magnetostatic and the Maxwell equation in the upcoming 3 lecture. But do not forget to subscribe the channel, like and share the session as well. And with this, I would like to thank you for attending the class. Thank you so much. We will meet soon and discuss magnetostatic. Thank you so much. Okay, so magnetostatic part 1 will be the next lecture. So we'll soon meet and discuss. Thank you.